very much. Thanks for the introduction, and thank you for inviting me here to share some of our recent work that we have done in this field. So hopefully you will enjoy it. So I will talk about ethylene epoxidation and how to use rational design. That's sort of the ending talk. I will spend quite a number of minutes trying to confine you in the model that we're using so you have some confidence in our results. So please stay tuned. So ethylene epoxidation, I think in this audience, we don't need so much of an introduction to the field. It's one of these chemicals that is base chemical for many of the different products that we need in industry. So it's a useful compound. It also has a lot of the fun properties, like it's colorless and colorless and sweet odor and so forth. So it's a valuable product that you need to design and find ways to do. It's the reaction as such has been known for quite some time, but also the process to do industry has gone through within the last 100 years development. So just looking at the base of the reaction, we know that it's exothermic, so you can do it. But as always in these partial oxidation reactions, we are fighting the thermodynamics of the reaction, overall reaction. So doing the desired product, we will gain energy, but also we are always fighting the complete oxidation of the reactants. So that's the challenge of how to do that softly enough. If you had the pleasure of joining John Lockmeyer's talk on 2 days ago, he was giving the introduction from the Shell company, what they have done, and of course the industry, the catalyst today is amazing. So you can achieve almost 90% of selectivity. So it's a very optimized process as such. And so we will see what we can contribute in that field. Am I standing too close to this one? Is it? No, good. So that's the idea. We will also start off with just a pure silver, trying to understand the basics of silver, and then we are fighting 50% selectivity. That's sort of the thing that we are fighting. As I said, the process is highly optimized. The patent for that process is almost 100 years, so a lot of development has gone into that product, that process as such. If we look from the scientific point of view, this since the reaction is very valuable for industry, this has also been a very high interest from the scientific society. And you can see the number of citations from the field. This is a recent review. And you can see that it has this exponential growth that so many other fields have, but nonetheless. In that article, they also list a number of challenges that remains for us to figure out. And I listed a few of them from the article. And of course, in this field, it has been quite a number of years that we have talked about what is the active surface, what is the active site, how does it look like under industrial conditions. So that's related to the two first points here. We also have what kind of reaction mechanisms, what are intermediates that are crucial for the reaction and so forth. So that connects to these two. And then how does the promoter works? What does the alkali and the chlorine, what does it actually do during these reactions? And then finally, why is silver the one of all the elements that is actually doing this reaction as such? I will sort of touch base on all of these listed problems. I won't go into depth of a number of them, but hopefully I will focus very much on this one and also say a little bit about the promoters, and mostly I will talk about the reaction mechanism and how we proceed through that maze of things that these chemicals can do. So just touching base on the oxide, on the catalyst as such under conditions, the operating conditions. So we have done, there are in the literature a number of studies looking at how does the oxide look like when it's under these conditions, the highly oxidizing conditions that we have in the reaction. And most of us are familiar with the phase diagrams that you can calculate from first principle, and you can correlate it with core-level shifts that is going on in the catalyst. You can have both the experimental and the theoretical combined to try to figure out how the surface looks like. And you can do that in different articles. This is our contribution. This is contribution from our colleagues at Chalmers and at Lund. But there are also a number of other studies throughout, and I want to particularly focus on the Christoph Uschi study a few years back. Excellent paper, really covering all the stuff that is going on and how that surface is really morphologically different as compared to the clean surfaces that we are sort of used to when we're working in this field. So in this article, they can really see and probe sublattice oxygen, different morphologies, very not so pristine and crystallized surface as we would expect. And that's probably very true as compared to what is going on in the experiment. We know that catalyst is a very light material. So of course we can imagine that during the reaction, the morphology changes quite a lot. So this is a study I would like to highlight. And there's also machine learning techniques from, for instance, Hellman that covers all the different morphologies you can have on pristine surfaces, how that is shaped, you can have triangles and so forth. So just the surface morphology is very, very challenging as such. And that is, of course, one of the complications in this field. How should we address? What kind of surface should we probe? But of course, being a simple-minded physicist, I typically try to ignore these things. So ignorance is bliss. We'll start from basics, see what we can learn, and then I will touch base on how our results connect to what is going on the catalyst surface. So first, we just take a look at what kind of reaction mechanisms do they exist in the literature, and I would highlight the Lincoln tool mechanism, where they very nicely show that the oxymethyl cycle is sort of the intermediate that you're looking for. So if you have that, you can actually have a description of how the selectivity and activity goes on this reaction. And from the article, they can also state that given this sort of, I would say simple, but it's not simply that way. But given that overview mechanism, they can actually handle activity and selectivity on these catalyst surfaces. So that gives us a description of how to handle this. Second mechanism that is known from the literature is the Zickelmann reaction mechanism. That's much more complicated. You have a number of different reactions going on, also subsurface oxygen or storage sites that you can store stuff. So this is a much more complicated reaction. But you can also then see that compared to experiments done for surface science, they get a very good agreement. So it's a reaction mechanism that capture most of the trends. But of course, the parameters are something that you can check with literature and also compare to experiment. But it's adjustable model in that sense. So what did we do? Well, oh, sorry. So I will just carry on. So this is, if you compare to all the experimental results over 5 orders of magnitude, the Zickelmann model captures that. So that's amazing. This is the model you're aiming for if you really want to design. So we want to compete with this model. And so what I will talk about is the first principle informed kinetic protocols. That's the first part of the talk. I will focus on that, and just to give you hopefully confident in what my results should be translated to. And then I will talk a little bit about the donuts, how we can view that what is going on. I will just touch slightly on, and then to the main part of the screen, finding a new formulation of the catalyst and see how that compares to experiments. See if we can beat shells. 100 years of development. I'm not sure, but we'll see. So this is the reaction mechanism that we have focused on. You see that as compared to Zickelmann's, it's slightly reduced. We don't have the access of the storage site. We don't care so much about that. That means, of course, that our results should be compared to highly oxidized surface, but not a surface oxide carrying surface. So they will be slightly different. I will try to point out when that becomes important. Otherwise, the reaction mechanism it follows the same. You activate the oxygen, that's important. And then it follows through getting that oxymethyl cycle group over here that can carry on to the ethylene epoxidation. But it can also do the acetite, so that's getting over here, so you burn it off. So that's sort of the competing reaction that you need to suppress in some way if you want to increase the selectivity. But then you also have a number of, in our case, lumped reactions that just burns off the reactants as such. So that's a reaction that you want to suppress in some. So this is the pathway we really want to perform. So let's see. Yes, breaking down on surfaces, we all know that you construct a surface in the computer and then you run the reaction. And of course, in all of these different surfaces, you can see that it follows more or less the same pathway. You activate the oxygen, it comes down, you dress it up, and then in the end you come to this transition state over here. So you get the OMC, and then you get to the transition state. And then it needs to choose which of these transition state pathway that it follows. And you can calculate that. As soon as we have the coordinates, we can always get the energy from using DFT. So this is what we did, and this is the reaction landscape that we had from that study. Now I separated the individual reaction landscapes here with one EV, so of course they should overlap. One, no, at zero, sorry. And you can then see that you have the activation barrier, and that's more or less the same on the different surfaces. Some are more reactive than others. But the main part is that only for the for the open one here, so that's the 100 surface, you actually have a favorable pathway to the ethylene epoxidation. For the other ones, that pathway is slightly higher than just getting to the AA product. So of course, yes, looking at the reaction landscape, you would probably say this is the favorite one. This is what you would go for if you want to have selectivity, high selectivity for SID. Of course, the reaction landscape is one thing. We need to do kinetics to understand what is going on under the conditions where this reaction happens. And before that, we need to figure out how does all of these reaction intermediates compete with each other. And since we saw that the oxygen oxide on the surface is important, how the silver is interacting with oxide, we know that the oxygen lateral interaction, for instance, the coverage of oxygen is crucial to get good agreement. And this is probably where our study sort of touch base on the oxidation of the catalyst, but also makes a more contribution of really handling the lateral interactions in a efficient way. So what you can do then is, of course, that you have the surfaces that you calculate, you can have different coverages, and then you can see the absorption energy of the oxygen on all of these surfaces. You see that some responds very strongly to the interacting oxygens, some were not so much affected by the presence of oxygen. So we need to model this in a good way. Now, the good thing is that Wolverton and Schneider, they introduced in this paper a very nice way to cluster all of these interactions into a formula. So we use the cluster expansion that they presented. You can then dig out all the parameters that you need to use to cover all the different circumstances that you need to have when you model the kinetics. So this is what we did, we paired it, and then you can see that overall the line is the cluster expansion and the dots are the data. So the cluster expansion captures quite well what is going on from the DFT point of view. And you can also immediately see that this is, you can almost immediately see what kind of coverages are sort of always present on the surface. So for instance, the 111 surface will have low coverage of oxygen, that's the favorable coverage. But then on the more open surface, you will have quite a number of oxygen on that surface. So just looking at that cluster expansion, you can immediately know what is going on the surface. And of course, there are other species, so we also included the lateral interaction of all of those species. And I can highlight that, of course, it's when oxygen is present on the surface, that's the main contribution. That's what you need to worry about. But since it's favorable, we can do all of these lateral interactions and plug into the kinetic quantical simulation vector. And you can see from the results that coverage of oxygen is sort of a present thing throughout. Another thing that is important for our study is that although now we have a good description of the coverages on the surfaces, we also know that the transition state of the different transition states, how they vary, that varies with coverages. This we also need to build into the model. So as the surface becomes more coverage, it will be harder to dissociate the molecule, for instance, and also the various varies. And that is what we do here. So not only do we have a good lateral interactions on the surface, we also know how the transition states vary with the coverage on the surface. So that goes into the model. And that was crucial to get the results I will show you. From there, you plug it into kinetic Monte Carlo, so you have all the list of the rates and you have the variance and so forth, and then you can see how the coverage expands with time. And here are some examples. Here are the conditions that I'm looking at. So it's almost 1 bar, and it's 540 Kelvin, and so forth. And then you can see the complete difference of the different facets. So on the 111 surface, you see that there are almost nothing there. This is not good for anyone that is colorblind, but the black ones, that's empty sites. And then there are a few red ones that tells you that there are some oxygen there. And you can also see the oxygen molecule showing up at the state. So this is just a snapshot once into the reaction. Whereas on the 100 surface, you see that it's very, very much coverage. So there are a lot of oxygen competing with each other. And of course, that means that those two surfaces, you can expect them to be different as compared to the rate and so forth. Okay, so that's the coverage. If you go into the rate and look what is going on, you can follow all the different processes. You can then, for instance, so just briefly, we will have a forward reaction on all of the reaction steps, and we will have a reverse step. You will have two temperatures shown in this table. So I will focus on the 540 throughout, so that's the upper bar. And you can see that in most cases, all of the reactions are in equilibrium with each other, or they could be in quasi-equilibrium. So only the oxygen dissociation and the ethylene epoxidation are different. They are having the pathway just going in one direction. So no competition there. And you can also see that this is the one on the surface, and you see that with respect to selectivity, it's the lower rate in both cases. And you can also see for the 100 that this is the one that will produce ethylene oxidation. Its selectivity is much higher on that surface. So that is sort of in the model. You can dig out all that information. You can also then calculate what is going on with the Toft, how much turnover frequency it is, and you can compare to experiments. So here I've taken the experiments from that Stigman used. So it's Campbell and Lambert did this many years back with surface science. And then, of course, you can see that in this case, we should focus on the purple. So in all of these experiments, it's the 111 surface. So sorry for adding the other surfaces. And so, of course, we see that our model, just for first principle, are not exact. That is for certain. I will be the first one to admit that the model is qualitatively okay, but quantitatively we are not competing with, for instance, the stimulants. So there are different things. But this is something you can adjust. But still, you're quite pleased. It captures quite a lot. Now we try to go through a number of things that I want to build your confidence in what we are doing. So, for instance, if you look at the top at other conditions, you can vary pressures instead of temperatures. You see that then our model agrees very well with experiments. The same is true when you look at the selectivity. And for instance, the selectivity you can compare to other measurements for the other surfaces. And we know from Christopher's and Willing's paper that cubes, for instance, have a much higher selectivity. And cubes are, of course, the 100 surface. And you can see that our model absolutely captures the same trend, although the numbers are not exactly the same. But overall, qualitatively, it looks okay. You can also then dig into what is going on with the rate control steps, the rate selectivity steps. Then you can see something that's sort of what we would expect from this kind of reaction. And then for the rates, so you define the rate like this, and then you can follow the different contributions from all of these, and you then see that, of course, it will be this one that handles the rates under these conditions, and it's also competing with the oxidation, or with the rating of the oxygen. So those two are competing, and of course, on the other side, the ones that are suppressing our reaction, that's of course the one that forms the AA complex. And you can also see that for the selectivity, it's always at that barrier when you choose either ethylene oxidation or the AA product. That controls the selectivity, which is sort of what we know from the beginning. So that's good to see that works. You can also vary more to industry conditions. And then you can see, of course, that under industry conditions, higher pressures, you're actually changing what is the rate controlling step. So when one reads the literature, one needs to be very careful what we compare to, and of course that shows up in the model. But we feel confident that this is a good thing. So hopefully I've convinced you that there are some qualities in our model. I was scared and surprised and also happy that tomorrow there will be actually a talk criticizing hopefully positively criticizing our model. And then just from looking at the abstract, so I can't promise that it's true, but looking at abstract, this is the experimental results. These are the two competing models. And as they are not doing the work. Maybe ours at least doing something qualitatively okay. They can also modify one of the stigmas model, and you add something with the surface oxides. So then again, our model, we are surely not including that part, the oxidation, how that subsurface oxygen and storage of oxygen. We don't have that in our model. But if you do, you can then make the agreement much, much better. But that's not the point for at this stage. Instead, I want to bring you from having all of these first principle stuff, all the surfaces. We want to do something. We want to add all the way to kinetic Monte Carlo, but we also need to do the microkinetics. If we really want to screen stuff, that's the end of the talk, then we need to do all of those length and time translations. And we were able to do that from the kinetic Monte Carlo. We could just the microkinetic model, so it has the same input values, and the agreement is very, very nice. The reason is, of course, in most cases, it's for the 1-1 surface, it's empty, so it fulfills all the microkinetic criteria. But also, you saw when you compare all the rate, the diffusion of all the adsorbates, that's very quick. So it fulfills most of the microkinetic demand. So we were not so surprised that it would work. So we have a microkinetic model that captures the first principle data and translates through all the kinetic Monte Carlo stuff. So now just touching the base on the dopants. So just briefly talking about what we did in that part, then I will go to the main story. So with dopants, we all know that just looking at the barrier heights, we saw that 50% would probably be the limit you would have if you increase the temperature. Selectivity should be 50% because the barriers are more or less the same. So that's fine. But then you have dopants, you increase the selectivity quite a lot. Now, how does that work? So what we did was to focus on the active sites and not caring so much what is going on in the stability assets and so forth. This is looking at the active site. And when you have one of these dopants, it can be the alkyl metals, you're introducing the diamond. And the transition state, when you choose between ethylene epoxidation and the AA, that has polarization that you can connect with the diamond that you generate on the surface. And you can then get a positive effect on the selectivity. So these are the lines where you compare the AA and the SE. And this is the 1-1 surface. So then you can see that the 1-1 surface favors the non-desired product, but as you increase the electronegativity of the alkalines, the selectivity becomes more or less the same. So this is a way to push selectivity towards making that product on one of the bad surfaces looking okay. And that connects very well with the dipole electronegativity of the alkaline matters. So we lose some activity, we see the barriers goes up, but we gain selectivity. Now, if you look for what is going on with chlorine, we have two options. We can have a chlorine on the surface, and that makes a very weak contribution to selectivity. But if it goes underneath the subsurface, that's not favorable from the DFT. So this is sort of speculative. Under reaction conditions, it's been experimentally reserved to be there. We don't see it in the energetics. But if we place it there, then it works. So just hand waving that it might be possible to generate all of these. And then you see, for instance, when you combine them, that overall you increase the activity and you also increase the selectivity. So the dopants are important and we can affect quite a lot on the surface. But one needs to probably figure out exactly how the structure is looking. So that's what I'm going to say about dopants. Let's get to the main story instead. So that's now we have microkinetics. We have the energetics. Let's see if we can find some new candidates in this field. This is, of course, very, very tough since the field has been existing for 100 years. So a lot of stuff is already done. We are, of course, stuck to periodic tables with a number of elements that we can choose from. And we pick these ones at first, so trying to build scaling relations. So on these metals, we could then calculate all the intermediates that we could have, and you could then generate the different reaction landscapes. And typically, it falls into 4 categories. You can either have the metal that is too inert, so it doesn't really work. You can, and that's this one, so gold, for instance. And you can have the best element, that's the silver, then the reaction landscape looks okay. But you can also have more reactant that burns off the different reactants into some products that are undesired. And all of that you can see in the diagram, but it's also shown in the figures. Now we will have the figures, we can of course try to adjust them with the BP relations and scaling relations. see what kind of descriptions do we need to have. One obvious one would be, of course, the oxygen absorption energy on the surface. That's normally a descriptor. And then you can have carbon. Uh, we will also have a combination of these to really more find the correct scaling rather than physical reason for why the scaling works. So in this case, we will have a combination that is 30 and 70% of the scales of these things. I'm not claiming that's capturing some physical or chemical property of the surface, but it's a data-driven scaling relation that captures the data. Given this, we have scaling relations just describing with two elements. You can see all the scalings looks good with formation energy, with all the electron interactions that we can have. The model seems to capture it. And you can also see what that gives as a result. You see that, of course, in gold, we expect the inert polymer reactive metals. Of course, it will be covered with oxygen. And now I should just briefly tell you that on these surfaces, if you instead construct, for instance, a surface oxide, the reaction intermediates energies looks almost the same as you would have here. So in our model, we will probably capture the right reaction landscape, although we don't have the correct structure underneath. That might be important for the size of it. But nonetheless, the model captures the oxygen coverages on the surfaces. And with the scaling relations, we then have the possibility of just calculating two parameters, the oxygen and the carbon absorption energy on all the metals that we would be interested in. And in this case, I think it was more or less the periodic table that the postdoc just went through and calculated all of this. And we can connect that to all of the barriers, transition states, and so forth, given it. So now we can then use the microkinetics. So we have a way to do that. We choose some temperature that was close to industrial relevant and was pressures that are close to industrial relevance. And then we can run that microkinetics. So we have a certain automatic setup to do that. And then you get some results. For instance, here I'm showing you coverage. Here is the coverage of oxygen. Here is the coverage of ethylene. And you can also see that the coverages depend very, very much on the descriptor that we have here. And of course, if you then were to look at activity and selectivity, not surprising, you see that it's almost always this kind of barriers where the reactants on the surface is sort of competing with each other. That's probably where you will find the activity and selectivity maps. You also see in this case that activity and selectivity are very closely mapped together. I'm going into more detail with the selectivity. So here is the selectivity map. And you can see, for instance, silver, green at the top, that's coming from the microkinetic, the scaling relation such. We see that silver is probably the best single element that you can have for this reaction. But you also see copper showing up down here. And we know that in the literature there exists a number of alloys between copper and silver that is actually improving this reaction. You can also see why gold is not really there, it's downhill on the volcano. And then you have a number of most reactive metals that are not really going to play a role in this reaction. It should be admitted that we are probably doing a lot wrong here because they should probably oxidize like crazy. But since they are sort of off the volcano top anyway, we don't care so much that we are missing some physics there. But there are a number of different elements here that we see are close to silver. So why not try to see if we can use those in more detail? So now we went actually more detail microkinetics instead. So now we calculate all the reaction intermediates for different compounds or alloys with these kind of elements. So in this case, we have a surface, we have the different alloys, metals, out of this family, and then we calculate all the reaction intermediates. We get the reaction landscape and an active site that composed of these alloys. And then you can calculate, for instance, the oxidation, the breaking of the oxygen, and also the formation of the ethylene oxidation. Oh, sorry, yeah, the ethylene oxide. And here, just show it, red is barriers, so that's always compared to silver in this case, and you can then see that the number of the alloys actually have a much lower barrier for the selectivity, so they will be favorable for that reaction. And also that the activation of oxygen is also favorable on these sites. So these are the candidates that we found, and we picked out just random kinetics, so we see that it's okay kinetics, it's formed within microseconds and so forth. So it fulfills all the criteria from the theory point of view that we are looking for. but can you trust it, right? So we have some elements and some trimer and metal that compose of these that looks very promising. Can we trust the results? Now, hopefully conveyed throughout the talk that we have a number of limitations. That's certainly true. There are DFT-based, there are kinetic-based, and it's model-based, and so forth. So hopefully, so unfortunately, we have a number of things that we worry about. I will then refer to that. Surely, we have a model, but sometimes we can dig out something that is important. And the good thing with physics and chemists is that we can test with reality. So we have the candidates from the computer simulations. We went to the chemists, asked them, could you produce this? And of course, chemists are the greatest people I know. So you'll always find some chemist that is willing to do cadmium and mix them together and do the measurements. So this is super impressive. So we had collaboration where they could synthesize this, and the main focus in this part was that it should be scalable. So whatever candidate we should have, it should be absolutely scalable. So no strange methods of doing it. So we went into the lab, synthesized, it's really good. So here you have the XOD spectra, and you can see that we form crystallines. We do the SAM and TEM, and you see that it's a crystalline surface, it's metallic in phase. So that's important, of course, when we compare, since we know that we are missing the oxide formation. So when we go to the lab, we want to compare to the sort of the more metallic form of particles. And you can form these. You can also look at signs. So when they go in these extra metals, it's so low limit. So we don't expect them to accumulate, and we don't see any traces of the alloys metals as such. So they are hopefully dispersed throughout the silver particle. And when you do the measurements, you can see that for the one that we identified as most promising, you can see that the selectivity is much, much better as compared to silver, and also the conversion is much, much better. So we have a candidate, so from the microkinetics, we could generate a number of candidates. It looks promising. When we go into the lab, they also come out as promising. There are some that are deviating. We said that they would be promising, but they were not so. So there are some limitations. In most cases, we could after analyze the experimental results and then see that it had separated during the conditions. So, but still, we were very super happy to have a candidate, and hopefully could be in contact with Shell at some point and see what they can bring, and I will take this further. With that said, I think I've come to the end. I've hopefully convinced you that we have first principle models based on the data, yes, first principle throughout, building model consistently, trying to compare to experiments and so forth, making sure that we have confidence, showing how we could scale that up with the microkinetics, and then doing scaling relations and the PEP, so we cover all of these things, find the promising candidates, go back to the more detailed ones, and then figure out that it works, and then finally coming to the experimental side, they can generate them, synthesize them, and then measure. And gladly enough, the candidates that we said were also shown in the experiments to be the promising ones. Now, of course, I'm glad to be out here presenting, but the hard work was actually done by all the other people involved, and we have the experimental people. But most definitely, I need to shout out for Matej. He's an associate professor nowadays, but he's a star. I'm voting for him. And he did all the work, so he should have all the thanks. With that, that's all for me. Thank you. Thank you very much. Thanks for the introduction.